Okay, we're talking about constant modulus algorithm. We've already discussed how it's great for doing timing recovery. And in that timing recovery example, there was really no distortion to the signal. There was just the timing that we had to recover. Now we're going to look at our shaped pulse, but actually introduce some distortion on it and see what CMA can do to equalize that distortion that was introduced into my shaped pulse. So we're going to first of all add a little noise, which we didn't have in our prior example. I was focusing on the timing aspects. I'm going to add still pretty strong signal-to-noise ratio of 25 dB, but I'm going to add distortion from a band-limited channel. So if this was my original shaped pulse, ideal sampling time mentioned here, when I put it through a low-pass filter, I'm going to distort the eye and so that it looks something like this. So the rails get very fuzzy because of this band-limited nature of the channel. Again, these are the analog sampling of the eye diagrams. But if I was going to sample them at, let's say, 3 taps, if I was going to equalize them, I could try and distort the try to combat the distortion that was introduced. And the CMA algorithm is a linear filter, and the linear filter has a certain number of taps. And depending on how many taps I use, I will be more effective in my equalization. And in this case, I have an example that's very, very simple, just a 3-tap equalizer. And you can see that I still have separation, a very thick rails for the plus and minus 1, and the eye opening therefore is relatively small. If I go to 11 taps, then I'm getting much better equalization. And I can go up to 21 taps. It's even better, but of course it's not as big a difference as I saw between 3 taps and 11 taps. And so in the laboratory, we can play with these numbers offline because it's an RTO, so we're going to play with them and see what kind of compensation we get. But we can see it's a function of the number of taps in my equalizer. So my CMA, effective at equalization, and how effective depends on the complexity I'm willing to put into it. Now, this particular CMA is using 1 iteration. So it goes through 1 time this convergence path. If I iterate and start my taps from the last iteration, I could get better convergence, and in that case 3 taps actually gives me some pretty good performance. This time I've done 5 iterations instead of 1. So we can see in the CMA algorithm, I'll be showing you the algorithm shortly, there's 2 options. One is the length of the filter, and the other one is how often I go through the process of blindly adapting my tap weights. So now I'm going to take some more noise. So the examples I gave you says distortion, but very strong optical signal-noise ratio. Now I'm going to go down to 15 dB signal-to-noise ratio, and that is going to, of course, have an impact on what the CMA algorithm can accomplish. So now, because of the noise, the CMA is still giving improvement, but the noise is not going away because of equalization. So the point here is that equalization is very effective against distortion, but it does nothing against additive white Gaussian noise. So noisier is going to have less of an eye opening than in the case where there was less noise.